When we see trees bending under a heavy gust, we are watching a massive, invisible mass of air rushing toward a very specific destination. To understand where that air is going, we have to look at the fundamental rule of the atmosphere. Air hates being crowded. It constantly seeks empty space, moving from areas of high pressure to areas of low pressure. This textbook diagram shows this rule in action. We have an inflated balloon connected to a flat one via a tube. Notice what happens when the connection opens. The dense, packed air in the first balloon immediately surges into the empty void of the second. Global wind operates on that exact same principle. A gust of wind is simply the Earth unclamping the channel between a crowded, high-pressure zone and an empty, low-pressure void. Since air needs these distinct zones to start moving, something has to be creating those pressure imbalances across the planet in the first place. Look at this model of warming air. As the particles heat up, they gain energy, spread apart, and lift off the ground. That upward escape leaves behind empty space at the surface, a low-pressure void. Conversely, as air cools down, the particles pack tightly together. They become heavy and drop, piling up on the surface to create a dense, high-pressure zone. A common misconception is that this rising or sinking itself is wind, but true wind is strictly the horizontal motion, the heavy, cold air rushing sideways along the ground to fill the empty space left by the warm air. Because the sun heats the Earth's surface unevenly, it acts as a giant thermal engine, constantly throwing the atmosphere out of balance. To see this solar engine operating on a massive scale, we can track the air along a typical sunny coastline. Water and soil react to the sun very differently. Solid land absorbs solar radiation and heats up rapidly, while ocean water stays relatively cool. This diagram maps the resulting pressure. Over the heavily heated sand, a column of hot air rises, leaving an empty void. Meanwhile, the cooler air over the water stays dense and heavy. Following the rule of pressure, the heavy ocean air surges horizontally across the sand to fill the void. Meteorologists call this daytime transfer a sea breeze. The afternoon wind hitting your face at the beach is the atmosphere rushing in to equalize the temperature difference. But watch what happens when the primary heat source disappears. Without solar energy, sand cools down quickly. The ocean, however, holds on to the heat it collected during the day for much longer. Now the system is inverted. The warmest air is over the water, expanding and rising, while the cold, dense air settles heavily over the darkened land. The heavy air over the beach pushes outward, rushing back out to sea to fill the new oceanic void. This strictly nighttime phenomenon is a land breeze. The Earth's surface temperature flipped, so the atmosphere reversed its flow to keep chasing balance. When these pressure differences become vast, the balancing act turns violent. This satellite image shows a spiraling cyclone where millions of tons of air are caught rushing into a massive pressure vacuum. At these extreme speeds, a counterintuitive principle of physics takes over, called the Bernoulli effect. It states that when air moves incredibly fast, its local pressure drops dramatically. You can see this effect during a severe storm. As hurricane-force winds sprint over the top of a structure, they create an intense, low-pressure vacuum resting directly against the outside of the roof. Inside the building, the air is still relatively calm and high pressure. That trapped air pushes aggressively upward toward the vacuum outside, effectively lifting the roof off from the inside out. The Cyclone aftermath is exactly what you see here. Coastal infrastructure completely hollowed out by trapped air trying to escape into a passing vacuum. Whether it is a catastrophic storm dismantling a building or a gentle afternoon breeze rolling off the ocean, the mechanism is identical. Wind is the relentless physics of a planet continuously trying to balance the scales.